Good morning, everybody. We'll just wait a couple of minutes before we start so everybody can join and we can get going, and then we'll get into the material. Whilst we wait, I'll just point out where all the exercise and lecture material is for the course today. You should already have a link, but in case you don't or you've not seen it or it's not obvious, I'll just share where it is at the moment. It's useful in case you want to look through the slides as we're going along, and because that's where the practical handouts are, so we'll need to go and have a look at those. So if I just share my web browser tab, this is the ARCHER2, the main ARCHER2 website. You'll see down here there's the performance optimization on AMD EPYC course. You can also get to it through this training link up here, and in there's a link to course materials, and that takes us to the main repository for the course. Actually, this main repository bit here doesn't have very much interest in it, but if you go to the 2022-12-13 branch, you can go in there. You can see that here's the timetable for the course. The PDFs of the slides that we're given today and tomorrow are in there, and more importantly, the exercise handouts, practical notes, particularly this one here to start with, are in there as well. So I'll put the link into a chat, but basically it's all on GitHub, but in a particular branch of the repository we're using here. We also have a chat, which I haven't opened up actually yet, for the training material, the training the course today. So on the ARCHER website, through where we got to the course materials from, there's this course chat, and here you can put some stuff in here as well. Now you can use the chat and collaborate like I've been doing as well. All of those are fine, but if you have questions, you can also put them in here.
Good morning. Sorry to interrupt. Should we push copy the hands-on to the ARCHER system?
You don't have to, because we have already copied the source. You can do if you want to sort of git clone the repository. That's perfectly fine. Actually, all the source code you need I've already copied into a particular location. So if we go into the exercise notes here, we'll see that the source code is already copied onto the ARCHER file system here. So you don't need to. Okay, if you want to, that's perfectly fine. You can just git clone the repository and then switch to this branch. But yeah, either is fine.
Okay, thank you.
No, thanks for asking. So good. I think we're pretty much all here. So I'll get sharing with the slides again, and I will turn my camera on just for now so I can just say hi. I won't keep it on forever or for long, because both my internet connection isn't brilliant and I find it distracting. But I just wanted to say hi to you all. My name's Adrian Jackson. I'm teaching part of this course, so I'm a employee at EPYC, and my colleague Mark Bull, who's around and about today, but is teaching the material tomorrow, is also teaching the course as well. So this is what we call single node optimization course, or performance optimization on the AMD EPYC processors. Really, there's lots of detail in how you would optimize for a particular processor. And this course is more of an introductory level, so we're not going to go very, very, very deep into how you optimize for a specific processor. What we're aiming to do more is give you an overview of some of the things it's useful to know about processors and nodes in general, so you can target your application performance at those, and then some of the specifics of the AMD EPYC processor that we're running on ARCHER2. It's an x86 processor, so a lot of the things we'll go through today here are common across the AMD and the Intel processors, and then there's some things which are quite specific to Intel as well. We go for that kind of balance partly because it's designed to be a general introduction to performance optimization course, but also because there is always a trade-off in performance optimization between making something perfectly optimized for a specific processor and impacting portability. So you have to change it every time that you want to move to a different system. So there's always a trade-off there. People, of course, will heavily optimize codes for particular processors when it makes sense to do that. But for a lot of the users on ARCHER2, there's a trade-off between the time and effort to optimize the code and the performance benefits required. Anyway, so this is an ARCHER2 course. All the material is online, as you've seen, hopefully. You can feel free to take the material and use it and reuse it and do anything you want with it, as long as you maintain this license that comes in here. I'm just going to give a brief overview of ARCHER2 to start with, and then we'll go into the course. ARCHER2 is a service which is funded by EPYC and NERC, so part of the UK research funding councils, for academic supercomputing, for academic computational simulation within the UK. These two funding councils, EPYC and NERC, have particular focuses on physical sciences, engineering, and weather and climate. So there are other computational resources in the UK for different fields like particle physics and things like that. But ARCHER2 is one of the big academic supercomputers in the UK. It's a service that's run by ourselves, EPCC, which is as part of the University of Edinburgh, and it's a Cray, HPE Cray supercomputer. We run the system actually in Edinburgh, and we operate it for the research councils. And as part of that, there's this funding for support of users. So what we call computational science and engineering support. And that involves people helping optimize applications or helping port applications to the system. And it also includes the training material around ARCHER2. So providing training to help people exploit this system in the most efficient way and best way possible. Interestingly, last time we run this course, the system was slightly different. So ARCHER2 went through a lifetime of changes already, where it started off as quite a small version of itself. So just I think 1,024 nodes to start with, which is like a sixth of its final size. A slightly different configuration to get us going. But now we're on the full ARCHER2 system here. So it's nearly 6,000 nodes of a Cray HPE system. Each one of those nodes has 128 cores. So that gives us nearly 750,000, or just over 750,000 compute cores. And for most of the system, there's 256 gigabytes of memory per node. There are some large memory nodes, which have got 512, but they're a small percentage of the system. Because this is a HPE Cray system, it uses Cray's network, so it's called the Slingshot Interconnect, which is their bespoke high-performance network. And then, of course, you wouldn't get anywhere without having some place to store data that you could need for input and output from your applications. So we have a bunch of file systems as well, mainly 4 Lustre file systems. It doesn't matter that there's 4 of them, but we have a number of Lustre file systems. Each project gets put on one of those, and that's where we store data that's generally used during applications running. So that's our work file system. There is also a burst buffer file system associated with it for speeding up some I/O for various applications as well. We're not going to look at the file systems particularly in this course, but that can be a bottleneck for some applications. So there are legitimate performance optimization approaches that you can take with utilizing and using the file systems efficiently as well. It's just that's beyond the single node nature of this performance optimization 2-day course. I should have said right at the beginning, feel free to jump in and ask questions as we go along, either through the chat or just speak to me. Don't be worried about interrupting the flow. I'd rather if things were not clear or not working, or for instance you can't hear me or my internet connection drops out a little bit, I'd rather you let me know. Okay, so just briefly, what is EPCC? I know many of you may already be aware of us, but some people aren't. We're a supercomputing centre at the University of Edinburgh. We've been running sort of national services and large-scale HPC systems for a long time, starting at the national service level back in with Cray T3D in 1994. But we do a lot more than that. We do training, we do master's programs, PhD students, and we do a whole range of research and commercial projects as well. ARCHER2 has a bunch of support material available with it, so if you're using or planning to use ARCHER2 in the future, then of course there's training courses, and there's all the material from past training courses online. We run virtual tutorials every month where people come along and present various parts of the system or various bits of work they've been doing, which can be very interesting. And there's a wealth of documentation on the system there. So looking at compilers and compiler options and MPI libraries and those kind of things, batch system, it's all there in the ARCHER2 documentation. So that can be useful. Just very briefly, who am I? So I'm Adrian Jackson. If you have any questions or follow-ups about the course, then here's my email address. So please do feel free to get in touch. I spend a lot of my time, I don't actually work on the ARCHER2 system most of my time. I spend most of my time doing research and collaborations with academics trying to get their applications to perform better, or looking at things like memory technology, file systems, those kind of things. But just like a lot of people in this kind of industry, we have a wide range of interests. It feels like I'm putting the cart before the horse here a little bit, so but there is a feedback form for this course, and the feedback is very useful to us. It helps us both assess, what went well and what went badly with training, what can be improved for the future, and those kind of things. So it is useful. We'll remind you again at the end of the course, and it's probably not worth filling it out just yet because we haven't done the course yet, but there is a feedback form from the website, or there will be by the end of the course, for you to give us feedback. It's not very complicated, and actually the main thing we need is the overall rating. So it can be done very quickly. After that, you can provide more detail, but you don't need to. So, but it would be very useful to us if you could fill that out at the end of the course. As I say, you'll get a reminder about that. If there are more general questions about ARCHER2, as I said, feel free to email me. But there's also a what we don't call a help desk anymore, a service desk here. With an email address called support@archer2.ac.uk. So any sort of questions can also go there as well. And if you're really, really interested in high performance computing, we run masters and actually PhDs on that topic, but we have a 1-year masters and a 2 years online masters to get really more in depth. And part of this is the kind of, this course is the kind of material we do on that masters, so performance optimization and profiling and those kind of things are things we teach on the masters. So anyway, if you're interested at all, there's a link you can go to. No, I'm going to correct that slide slightly because I put 19 and it's 91. It's a little typo there, apologies. I'll go and share that again. That changes every time we run the course, which is why it's not correct this time. So apologies. So for the course today, some of you may already have ARCHER2 accounts. That's perfectly acceptable to use the accounts you already have. For everybody else, we've provided you with the option to sign up for an account, and hopefully most of you have gone through and done that. If not, now is a good time to go and do that. You should have instructions in an email from the ARCHER2 training people from Cray telling you how to do that, and I can approve the accounts once you've done them. The reason that we use these accounts is because we want to give you access to a system, because we want to run experiments and practicals as part of a learning. So we've got a full set of bits of software to play around with and bits of code to do write or change. And so having a place to run that and collect performance data and do profiling and analyze things is important. As I say, if you already have an ARCHER2 account, you can use that. We set up reservations for these courses, which we can use to make sure that we can run our jobs quickly. But actually on ARCHER2, there is what we call a short queue, which is pretty quick anyway. So we don't tend to necessarily need those reservations all the time. So if you're going to use your account, just use the short queue to run your jobs, and you should get on fine. If none of that makes sense to you, then don't worry at the moment. We'll come back to it in the practicals, and you can also ask questions along the way. These accounts have a certain amount of time in them, so you can run applications on the system. We probably won't use all that time up today. The accounts will stay open for longer than the course. I've put 2 weeks here. I think it may be slightly longer than that even, but you can experiment a little bit with ARCHER2 out with the course, outside the course, after the course, if that's useful, because these accounts will stay active for a while. At some point they will close and you'll get an email telling you that's going to happen. And so before that point, if you really want to keep any of the source code or any of the exercises we've done, it's worth copying the data off the system at the end. But all the generic stuff is available online effectively forever on the ARCHER2 website and on GitHub. So it should all be there for you. All our courses have a code of conduct and applies both to me and Mark as people training you and people attending, which really boils down to just be nice to everybody during the course. It's less problematic, I think, in an online course, but just be aware that by attending this training course, you're expected to abide by this code of conduct. And if there's any problems that arise from the course, there is an incident reporting form online which you can use. And just before we get started proper, it's worth pointing out this is probably of more interest to UK academics. I know we've got a wide mix of people on this course today, and partly because it's a praise course, but there is a funding stream associated with ARCHER2 called ECSEs, Embedded CSE, which allows people to ask for time for people like me to work on their codes to improve performance or add functionality, or ask for money to employ somebody locally to do that. And so this is quite a nice funding scheme where you can ask for up to 18 months of effort to do any of these things on the slides, from implementing algorithmic improvements to porting to adding new functionality to existing codes. And so that can be quite a nice scheme it's often quite hard to get this kind of work funded in the UK through the research councils. And so this can be quite a nice way of doing that. If you've got any questions or interest in that, then again, drop me an email or contact the help desk, the service desk, which we can sort that out. Okay, I should also give a couple of slides about Praise. I'll do that after this because this is also a Praise course, and so I should just give the generic slides about what Praise is as well. But before we swap to that slide deck, this is what we're going to go through today, and I'll be teaching you these. So lecturing and looking after you on the practicals today, although Mark is around and will help out with the practicals. So today we're going to look at the ARCHER2 node architecture. So what hardware is in the nodes, what hardware is in compute nodes in general, and how they can impact performance. We'll do a little practical, 10 to 11, where you just take a code and you run it. And this is really to get you up and running on the system, make sure you can compile jobs and run them, make sure you can access the system. And inevitably, people always run into problems trying to access ARCHER2 or any remote system. So that's where we can debug some of those kind of things. We'll have a break 11 to 11:30, and then we'll go on profiling and do some profiling work. Break for lunch at 1 o'clock, and then look at optimizing with a compiler up till 3. There's a break 3 till 3:30, and then the rest of the afternoon is just working through a little profiling and optimization practical. Okay, so I'll be around from 3:30 or from 3 up till 5:30. But if you'd rather go off and do this in your own time and just pop back in and ask questions later, that's perfectly fine. So we've not got any lectured material after 3 o'clock, so you can handle that how you would like. And then tomorrow, Mark's going to take over, and the morning is OpenMP optimization, so optimizing parallel codes, but still on a single node. And then after that, Mark will be looking at vectorization and memory hierarchy optimization. So this is looking at some of the features of the parallel functionality inside the CPUs to see how you can efficiently use that for applications. Actually, I should have asked Mark, he may have wanted to swap some of these things around, because to me, conceptually, the vectorization stuff comes first, and then the OpenMP stuff comes second. And I think we probably swapped this around for staff availability last time. But anyway, they're all similar length activities. So if Mark wants to swap them around, I'm sure he can. As I've already pointed out, all the slides and exercise material is online at GitHub. The link is here. It's also in the chat. So you can go there. These are some pictures of ARCHER2, by the way. So this is ARCHER2 sitting in its machine room. Actually, it's not a huge, I mean, it's a big machine room, this one, but it's not a huge system in the end. I think it's something like 22 cabinets. All the electrical stuff around the outside. And then the picture on the right-hand side is all the cooling that's running in. So hot and cold liquid passing into the blades to get the heat out of the system, which is obviously one of the challenges for something like a big high-performance computer. And then on the left-hand side, this is networking, actually mainly all optical networking between cabinets, because inside a cabinet, all the networking is done on hardware that's directly inside on copper that runs on the backplanes, so you don't really see it. And we'll come back to this slide when we get to a practical session, so don't worry too much about that. So hopefully this course will be useful and enjoyable for you. As I say, there's a chance to provide feedback at the end, and we welcome that feedback, both positive and negative. And please do ask questions as we go along. We aim to make this material as understandable as possible, but it's always within the bounds of what I already know. So I may assume you know things that you don't know. It's always within the bounds of how clear I am as a speaker and how clear the material is. So at any point, if things don't make sense, then please do ask, because usually it also means other people won't know, and it's helpful for everybody in general. So I'm quite happy to go back and discuss and elaborate on things. Yeah, okay. Predictably, we're running behind already, but that's fine. I've got plenty of time built into the schedule for that. Let me see. I'm going to see if I can just get a quick set of praise slides to give an overview of that. But whilst I'm getting that up, are there any questions in general about the material or the introduction so far? If not, that's fine. I'll just give a very quick intro to Prace, because Prace is part funding this course. Although I think that's our last, I'm told it's our last Prace course of the moment, which is interesting. So let me just share this slide again. So this course is partly funded by Prace, which is a partnership for advanced computing in Europe, and EPYC is part of Prace. It's a Prace Advanced Training Centre. The PRACE is a European collaboration. Obviously, with the United Kingdom no longer being part of Europe, that's slightly strained, but we're still an advanced training centre under a PRACE umbrella at the moment. And it's designed really to provide access to high performance computing across Europe. So to share systems across Europe and to provide the expertise to access those systems and use those systems efficiently across Europe. So just like the ARCHER2 service, which provides training alongside access to systems, PRACE does exactly the same thing. And there are a bunch of training centres associated with that, of which EPYC is one, but there are a number of others around Europe. This course is coming under the auspices of that. So we also give the same course in the UK just to ARCHER2 users and to UK academics, and then of course it's highly likely they'll go on to use the ARCHER2 system. As a PRACE course, a lot of you may then go on to do work on other systems, not just ARCHER2, but that's also fine because the general optimization material and performance material is applicable across all of them. And then there are a bunch of systems around Europe which are very similar to ARCHER2, if not the same. So, for instance, the HLRS large-scale system is it's not a Cray HPE system, but it has the same processors in very similar node configurations. And there will be a number of other systems around the NUMA systems in Finland, the large ones there. They have GPUs in them, but they also have AMD processors in them, which are similar but not the same as the ones we have. So the general material and the general approach should be applicable across the piece. Okay, any questions? I should say we're recording this as well. We generally record these courses and put them up online for people to view later as well. If you have any issues with that, let me know, but it's recording at the moment. Okay, so let me go on to the single node, to the architecture, the node architecture lecture, and we will whiz through that and then see if we can get you up and running and doing practicals on the system. We'll just wait till that comes through. Okay. So what we're going to look at is what does a compute node look like, and where are the issues that performance that affect performance or can be changed to impact performance. Where do they come in? Fundamentally, if we look at a HPC system in general, a large-scale computer, there are four main bits we can think of as being core components that make up that system. So processors, which take data as input, do some work on it, and produce data as output. We have memory, which is used to store data whilst it's being worked on. Then we have interconnects or networks which connect these HPC systems together and to the outside world. And then we have storage, which is for long-term storage of data whilst it's not being worked on. And this can store data over time without power. That's the sort of the main difference between that and memory, because memory requires electricity to keep the data there, and longer term storage like disk drives and tapes doesn't require any electricity to keep the data there. It may require some electricity to access the data, but not to keep it there. Because we're just looking at single node optimization, we're only going to look at processors and memory, because the interconnects are important and the storage is important, but they're about the whole system in general and connecting multiple nodes together, right? And so we have other courses. If you're interested in optimizing the network, we look at that in some of the advanced message passing courses. If you interested in the storage stuff, we also have courses that will look at optimizing I/O or doing I/O in different ways. And they're both important for applications, just not the focus of this course. As I said, the main workhorse of these nodes is the processors. On ARCHER2, we have 2 processors per node, but they have a simple, if complicated, task to do, which is to take data, perform instructions on it, and store that data out again. So a processor will generally load some data in from memory, work on that data in local memory, and when it's finished, it will store that data back out to memory. The work of a processor is performed on values in what we call registers, and registers are just a form of memory, which is local to the processor and runs at the same speed as the processor. And once the data is in a register, then it can be worked on very efficiently. The challenge we have, and I'm getting ahead of myself here, but we'll come back to this, but the challenge we have is that building registers, building memory that stores data that can be accessed and used at the speed of a processor is expensive. It's expensive both in terms of the number of transistors you need to use to do that, and it's expensive in terms of the amount of energy it consumes. So we are limited in the amount of memory we can put directly into a processor which runs at the processor speed. So we're limited in the amount of these registers that are available to us. So typically a processor will have, somewhere between 60 and 100 registers. There'll be separate ones for integer numbers and for floating point numbers, but that's the local storage you have. Now, I should have said at the beginning here, I'm going to get you confused a little bit. I'll confuse myself a little bit in the terminology I use about the processor. If we go back far enough, if we go back 20, 25 years, then a processor was a single monolithic thing where it had a single set of functionality in it, and that was it. Of course, nowadays we have multi-core processors. So each processor has many cores. On ARCHER2, each processor has 64 cores. And in this aspect, when I'm talking about registers and saying there's about 60 to 100 registers, that's per core. So of course, in the whole processor, there's 64 times that. But it's still, each one of those set of registers is private to that core and is limited in size. Anything we need to get to work on needs to be loaded in from our main memory, which is much bigger but much slower, into the registers, and then worked on and then stored back out again at the end. Processors are very complicated. They have different functional units. So they have integer units to do integer work and floating point units to do floating point work and branch prediction and all these kind of things. But fundamentally, for computational simulation and for machine learning, you're sort of limited by 2 things in performance. One is the clock speed of a processor, so how many instructions it can run a second. 2 gigahertz, say, or 10 gigahertz, or somewhere in between. And then the peak floating point capability, because for most computational simulation things, and for most machine learning, it's floating point arithmetic, which is primarily used. So that's what limits performance. Of course, the peak floating point capability is linked to the clock speed, but may have some multipliers of the clock speed. So we'll come on to see you may have floating point units. You may have multiple floating point units per processor. Each may be able to do multiple instructions at once with vectorization. Each may be able to do special instructions that do things like an add and a multiply together. And so that gives you your overall peak floating point capability. I should also say that for most applications, you never get anywhere near the peak floating point capability of a processor because you're limited by other bits of hardware which is slowing down the program. Generally getting data to and from memory, maybe getting data to and from storage, maybe getting data to and from the interconnect and network, and for other structural things inside the processor. But yeah, the clock speed determines how quickly instructions are executed. We went for a lovely period in you know, the 80s, 90s, early 2000s, maybe not really, where the clock speed would go up every time a new processor came out, and that meant your program got faster because your processor could do more instructions per second, and so your application would just run more quickly. The processors have tended to plateau out at somewhere between 2 and 4 gigahertz now, and have not really significantly improved beyond that. That's generally because there's a power limit to how much power you can get into, or maybe I mean energy. There's an energy limit on how much energy you can get into a processor and how much heat you can take out of it before you damage that processor. And as you put up the frequency of the processor, the clock speed, that proportionally increases the amount of energy that's going into that processor. And there was a way to get around that for a while, because the energy required for the processor is proportional to the clock speed and the voltage of the processor. And the voltage being the difference between the ones and the zeros in our binary logic. And so what you could do over time was reduce that voltage, so there was a smaller difference between a 1 and a 0, but that proportionally that kept the energy the same as you push the clock speed higher. But unfortunately, we get to the point where we can't really reduce that voltage much more, because you reach the limit, the switching limit of the transistors effectively. So so we don't see at the moment, without maybe step changes in the kind of silicon transistors used over time, or the kind of technologies used there, we don't see the clock speed significantly increasing at the moment. But we do have multiple cores going on to the processor instead. Okay, so inside an individual core, we have the different functional units we can use, and then a whole set of hardware optimization that goes on in there, including things like pipelining, out of order execution, speculative computation, all these kind of things, which we'll touch on. Because we can't push the clock speed up, but people have got better at squeezing transistors into space, into a fixed amount of silicon, by improving manufacturing approaches and techniques for transistor manufacturing or processor manufacturing. We have been able to put more things on the processor. This is the multi-core thing. So, you know, you'll probably all have heard of this thing called Moore's law, which is really Moore's rule, which was stated that, you know, CPU power doubles every 18 months. So what he really said was the amount of transistors you can fit in a fixed area of silicon doubles every 2 years, something like that. And of course, with more transistors, you can add more functionality to your processor. Some of that you can use to increase performance by increasing functionality on the processor, which increases parallelization to the number of things you can do. And so we've gone through pipelining, which is running multiple instructions at once on the processor, through to medium grain parallelism on the processor. So that's where we do superscalar. This is issuing multiple instructions at once to different functional units in the processor, vectorization and hardware multithreading. And now we're at sort of multi-core on the chips, so coarse grain parallelism. So what we see nowadays is processor manufacturers are still innovating on transistor density. So people are squeezing more cores onto a chip. So ARCHER2, the first system like this, had 2 processors per node, and each one of those processors had 12 cores. So you had 24 cores per node. Now ARCHER2 has 2 processors per node. Each one of those has 64 cores, so you get 128 cores per node. So you can see that the number of processors per node has not gone up, but the individual number of workers in there has. Of course, this means to really exploit a node efficiently for applications, you need some level of parallelism to be able to do that. So you need some level of being able to use all those cores at once. And that's where the OpenMP thing comes in, which Mark will talk about tomorrow. That can let you use those things, and there are other ways of doing parallelism as well. No, give me a second. Let me just get that back. As I say, feel free to jump in with any questions if you have any. And whilst I share again. So if we look at the inside the individual processor itself, we'll have these multiple functional units. It's a basic building block of the processor. These do vary by processors. So, you know, an Intel Xeon processor of particular flavor may have different number and configuration of functional units to an AMD processor. But fundamentally, we'll have a unit which is responsible for fetching, decoding, and dispatching instructions. So this is what runs your program. So there'll be an instruction unit, and then there'll be maybe one or more integer and floating point units. So things that do integer arithmetic and things that do floating point arithmetic. And the floating point ones are the ones that are obviously key for a lot of computational simulation performance, because they do the arithmetic operations that are required for computational simulation of machine learning. But there will also be other things in there, so control units which will do program control flow, so branches and jumps and branch predictions. There'll be load store units which load data in from memory and store data out to memory, so they interface with that data we need. And then there's the register file, which is storing the data that we're currently using for a given application that's running. So that's sort of keeping track of which registers, which local storage in the processor my application is using. There's also a lot of other functionality in there. So memory management, cache controllers, bus interfaces, graphics, multimedia, all that kind of stuff. But for most applications that we're looking at and looking to optimize their on-node performance, then it's sort of these are the main ones we're looking at. These are the things that will restrict performance or functionality or impact performance. And then we'll go through this in a little bit more detail for each one of these things that are implemented using these functional units. One of the key things for modern processors is the idea of pipelining. So that instructions can be broken down into stages, and each stage can be executed in one clock cycle or a set of clock cycles. And so you can have many instructions running at once using different parts of a processor and moving through that processor, so we're not having to wait for one thing to finish before we can move on to the next thing. So this is sort of core to modern processor design and performance. And it allows you to complete multiple instructions, one instruction per clock cycle, even though individual instructions may take a number of cycles to complete. Okay, for the AMD EPYC ROMs that we're using on ARCHER2, we have a 19-stage pipeline. So there'll be 19 instructions to get good performance. There'll be 19 instructions in flight at any one time for a core. There are some restrictions to these, so not all things will fit nicely into these pipelines. So there are things like floating point square root, floating point divide will not necessarily pipeline easily, so they can have a performance impact because they break this pipeline in. They mean you can't have these 19 instructions in flight at once, so they can reduce your overall efficiency because your pipeline drains down, you've got less work coming through and these kind of things. So there are a bunch of instructions which can impact this in terms of the performance. And that performance impact is experienced with this idea of every time you have to stop or start the pipeline, you waste cycles because it takes a while to fill that back up with instructions, and so you'll have a point where you've got nothing completing at any one time, and that's a waste of processor cycles. You can have these what we call pipeline stalls for a number of reasons. One of them would be that you're trying to do some instructions that don't pipeline, like the floating point square roots or the division. It could be that all the instructions you want to run want to use the same hardware units at the same time, and so there's no option to overlap them and do different things. And then you can also get these stalls because of data dependencies between pipeline instructions and structural dependencies, so branches in your program. To get around these things, the modern processors often have what's called out-of-order execution, particularly the x86 processors have out-of-order execution. And this is designed to minimize these pipeline stalls. So basically, the compiler will generate the code in a certain order, and then when those instructions get loaded up in the processor, there'll be some hardware there to decide the dependencies between them, and then try and schedule them so the pipeline can be as full as possible whilst maintaining those dependencies. And so some of the cleverness in the processor silicon goes into this out-of-order execution functionality. Now, not all processors have this functionality, particularly some of the ARM and the RISC-V ones that are coming out are not necessarily out-of-order executions. But for the long pipeline x86 style processors, this is sort of key to getting good performance. You don't need to do anything about this, right? This is all done for you by the compiler and then by the hardware, but it's worth being aware of because you can restructure your code sometimes in ways which help this kind of pipeline issues, particularly if you have particular pressures on particular functional units or stalls in the pipeline, which you can see in the profiling data. It may be that if you can separate out functionality into different loops, you can merge loops or you can split loops, or you can tile some of the loops, because loops are one of the key functional units of our computational simulation applications. That can get you around some of these performance issues and reduce some of these pipeline issues that you see. How about you may see? There's also sounds like a question. Oh yeah, if you've got a question, just let me know.
Hi, I got one question regarding the number of pipeline stages. How do you actually count the number? I suppose it's from like the fetch of the instruction until retirement, but how do you count them when there is like multiple execution units and out of order execution? Like what did 19 really mean in this sense?
So in this sense, it's the 19 is effectively what we look at sort of like dispatch points. So it doesn't mandate that you have to necessarily go through particular functional units. It just mandates that there's a load from memory, load instruction, decode instruction, execute instruction on particular functional units, wait for instruction results. So it's that kind of pipeline. It doesn't specify these are the specific functional units that you're using, but it specifies the stages a particular instruction from a program will go through when it runs through the processor. There is sort of quite detailed documentation on each one of each pipeline, so I can point you in the direction of the AMD ones if you want to get more detail on that. But it's more, it's not fixing exactly what functional units are used, but it fixes the points where an instruction goes through different changes as it moves through the processor.
Okay.
Does that make sense?
Yeah. Just I was a little bit confused because it's my understanding that these functional units themselves can be pipelined and like
right,
and they doesn't have to have the same number of stages. So like which path do you take, like the longest path or the average, shortest? Like that, but that's a technical detail, maybe.
Yeah, no, it's a good question. I'll look out some material on that, and if you drop me an email, I can send you that separately.
Yeah, okay.
It gets a little bit complicated. In general, it's about the variable wait time on those kind of things is not. So it's usually the shortest path that you would use, and then there can be slightly longer paths because of longer floating point, generally longer floating point delays. But at the same time, there can also be longer paths because of memory operations as well. But it's generally the shortest route you take.
Thank you.
No worries. Yeah, so there's also functionality in processors to do branch prediction. And actually, you may have noticed in recent years, there's been problems with this kind of functionality because it's led in Intel and other manufacturers' processors to security issues, to bugs in the thing where you can actually access data you're not meant to be able to, because there's functionality to do what we call branch prediction. So because you want to keep this pipeline full all the time, that gives us best performance. Actually, we sometimes need to guess what instruction to run next, because the outcome of a branch, and a branch in this case could be an if statement or it could be a loop. The outcome of a branch hasn't actually been calculated yet in the code because that's still running through the pipeline, and we need to decide what instruction to run next. And if we waited for that branch to be completed, we'd drain down the pipeline and we'd lose our performance. So branch prediction speculates which path in the code will be taken next, and that can be done based on various heuristics and collecting data over time of what's happened as the code's been running. And then it will do speculative execution where it says, okay, do this set of instructions next, but be aware that if I was wrong about where this branch would go, we need to cancel those. But as long as your branch prediction is pretty accurate, and it will be for things like large loops, then you can speculatively execute large amounts of code without having any performance penalties. We can keep our pipelines full, and that's all done in the hardware for you as well. There's also functionality to do what we call instruction level parallelism. So pipelining is a form of this. We can have multiple instructions at once. But also modern processors will do what we call superscalar instruction level parallelism. And this is not just having a pipeline of instructions, but being able to use all the functional units on the processor at once. So the floating point units and the integer units and the load store units can all be in operation every clock cycle. And that's what we call superscalar instruction issue. In issuing more than one instruction that uses a different functional unit at the same time. And that's, again, the superscalar stuff for us is done in hardware. And there's things we can do in our codes to help compilers and the hardware optimize for that. So things like making sure there's a good instruction mix inside the inside any loops we're doing or any program we're doing, if we can. You know, you're always going to be limited by what your application's wanting to do. If it's always wanting to do floating point operations and hardly doing any integer stuff, then you're not going to be able to exploit those integer units, but then you don't need to, so it doesn't help. If you've got lots of mixed integer floating point and you can mix them in the same loops, for instance, and that can let you use both those functional units at once. The other level of instruction, the other class of instruction level parallelism that we have commonly in processors these days is vectorization, or SIMD parallelism. And this is the idea that individual functional units can actually execute multiple instructions at the same time, as long as they're all doing the same thing. And this is a vector instruction. Now, vectorization and vector hardware is not new. It's been around for a long time. What is new these days, in the past 10, 15-ish years, is that it's commonly inside a processor rather than being a design of a system that goes across a whole machine. So it's inside a processor, and it means that the floating point and integer units generally nowadays are vector capable, so they can run multiple instructions at once. And we'll come on to look at what that means in more detail. So yeah, these are superscalar processors. Again, you don't have to care about this necessarily as a programmer, but when you start to come to try and get the best performance out of a processor, then you may be looking at how many instructions you retire every clock cycle, and you may look at which functional units are heavily being used and see if there are any ways you can optimize there. But that's sort of quite at the far end of the optimization cycle. We've got lots of things to get through before we get to that point. And this is all done in hardware for us. The vectorization stuff is this idea that we could do multiple instructions at the same time as long as they're doing the same thing. And it comes back from the design of the floating point units. It turns out that it's pretty easy to replicate the arithmetic part of those and chain them together without having to do very much more in the silicon. So you can make them bigger than your normal operation size without having to add huge amounts more to the silicon. So the idea here is, instead of doing a C equals A plus B, we can do a C equals A plus B and an F equals D plus E at the same time in a single instruction. Modern processors all support this. On the x86, so the Intel and AMD architectures, you're looking at the AVX instruction set. Latest Intel CPUs are AVX 512. These AMD ones are AVX2. Newer AMD CPUs will be AVX 512 as well. And then, but we also have it in things like the ARM processors with the SVE instruction set as well. And so these are new instructions in the language which are generated from your code. And they have to cover the arithmetic operations, so integers, floating point arithmetic, but also load, store, and comparisons as well. And then the processor needs additional vector registers, so special registers to store this data in as well. But if it has all that, then it can do vector operations. And so effectively what you can do is 4 floating point adds at the same time instead of 1 floating point add. So it's 1 instruction, but it works on 4 separate bits of data and produces you 4 results at the same time. And this lets us improve our floating point performance on the processors. There are restrictions on how you do vectorization, and Mark will go into much more detail tomorrow on the vectorization stuff. There are restrictions there in what the hardware can do and how you can exploit them. But getting good performance out of the vector units, if you can, is key for modern, for getting the best floating point performance out of modern hardware. One of the keys, anyway. There's restrictions around memory layout and memory addressing and things like that. And the operations have to be independent. Now, in general, we can also rely on the compiler to do this for us. So in general, we don't have to do necessarily write vector instructions in our code. It is possible. You can write with vector intrinsics, but it limits the portability of your code if you do that, because those intrinsics are likely to be only limited to a subset of processors and will change over time. So the compiler can identify and generate vector instructions for you. But the compiler is pretty limited in what it'll do. So it'll only really do loops, and only loops of a certain layout and definition. Now, this is good for computational simulation because we have a lot of loops, but there are definitely things you can do structuring your code and structuring your software that helps the compiler spot where it can do vectorization. And if it's not managing, there are things you can do to manually do the vectorization to exploit this functionality in these hardwares. And then, of course, we have multi-core chips. They are commonplace on processors. We can consider, in general, an individual core as our functional unit, as our main processing element, just at that level. But it's worth bearing in mind that quite often some resources are shared between all the cores or some of the cores on a processor. So some level of caching, we've not talked about caches yet, but quite often there's some shared cache between cores. And sometimes, not on the processors we're using here, but sometimes you can even be sharing floating point units between cores. This can be both a good thing and a bad thing. So if you structure your code correctly and you're doing parallel stuff, then that shared cache, last level cache between the cores can let you do quick communication between local workers in your parallelization. But it also means that other other work on other cores can impact your performance. So it's just something to worth bearing in mind for application design. What are caches? Since we've started mentioning caches, well, we have our cores, which I've labeled up as CPUs up here. And then we've got main memory where our data is stored down the bottom here. And the thing to bear in mind is that main memory is much slower than our processor. So up here we have our processor and it's got its registers, and those registers run at the same speed as a processor. And then down here we've got main memory, and it runs something like 1,000 times slower than the processor. And that's because it's not because we can't build main memory that's as fast as a processor, but the technology we need to build memory which is big runs much slower than the technology we use up here in the processors to build memory which is as fast as a processor. So main memory is larger in size, lower in energy and heat production, but much slower than the processor. And of course, if we have work that's going on here in the processor, which is waiting for data to come from the main memory, and that's 1,000 times slower than the CPU, then we're going to be waiting 1,000 cycles before we can progress that work. And that would mean that our performance of our program and our applications would just be terrible, because it would always be a minimum of 1,000 times slower than the processor itself could actually run. So to get around this, there are some intermediate memory levels of memory between main memory and the processor, which we call cache. And these are slower, not as fast, but still very fast, small amounts of memory, which we can use as local storage, which the CPU can come to and talk to when things don't fit in its registers, go and get the data, but it doesn't take anywhere near as long as the 1,000 times slower it would take to go out to main memory. So you could go, and generally there's a number of levels here. So we have a small level 1 cache directly on the processor, which is not much slower than the processor. Say a latency of 10 cycles to get something from L1 cache. So it's sort of 10 times slower than registers, but still pretty quick. In a 19-stage pipeline, if we've got a latency of 10 cycles, we can get data in from the cache within that pipeline stage, so we can effectively work on our data without losing any CPU performance. But that's small. And so there tends to be another couple of levels, an L2 and maybe an L3 cache level, which are progressively bigger and progressively slower. So generally each core will have an L1 cache. There'll probably be a shared L2 cache between some cores on a chip, and then a shared L3 cache across the whole processor or something like that. These again are all automatically managed for you. Your data moves in and out of these transparently to your application, but making sure that you can efficiently use these caches if you can is again key for good performance. So making sure that you reuse, so caches work on these two principles, both principles of locality, temporal and spatial locality. They work on this idea that if you've used some data recently, you'll probably use it again in the future. And if you've used some data located close in memory to another bit of data, then you'll probably use that other bit of data soon. Okay, and this is how they generally get the performance. In a multi-core level, there's some contention for the caches. So your L1 caches are private to your processor, but all these L2 and L3 and main memory bandwidths will be shared with other cores. So there can be some performance interaction between the work that's running on different processors here as well. And some of that stuff you'll see in the OpenMP and the memory hierarchy stuff we'll look at tomorrow. Mark will teach you tomorrow. There is a set of other functionality on the processor. So what we call hyperthreading or superscalar or multi-threading, which is this idea that maybe we don't just have to run one thing on our core at any one time. Because modern processors are superscalar, because they can run multiple functional units at the same time, but not all programs will use all those functional units because of the way they work, it is possible to add a little bit of extra hardware to do hyperthreading or simultaneous multi-threading which lets you run 2 programs at the same time on the processor. So to mix the instructions of 2 programs at once on the processor, rather than just having 1 program's instruction on the processor, in the hope that each program's instructions will be using different functional units, and so you can overlap them at the same time. Okay. The nice thing about this is it doesn't require that much extra hardware in the processor, so it requires some more registers and a bit more logic to support those registers. But other than that, it's pretty low level, and then everything else can be shared between those threads. So the example here is, if we can consider each of the columns of these pictures as functional units, so that could be like the integer unit and 2 floating point units, and a load and a store and a branch prediction unit. And then each one of these threads, the blue thread and the red thread, each cycle time, that's what the rows are, is using a different set of functional units. Okay, and we can see there's gaps in here because each application, each thread is not using all the functional units all the time. And so if we can overlap these 2 things, then we can, given this configuration of functional unit usage, we can actually run both threads at once, only requiring an extra instruction cycle to get 2 times the amount of work through. Okay, so this is the theory behind hyperthreading or simultaneous multi-threading. The reality is, for a lot of things we do, it's not actually that beneficial, because for a lot of our applications, for large-scale parallel applications, and actually they're all doing the same thing at the same time. So they're all trying to use the same functional units at the same time, and so you don't end up with any benefits there. So in practical, you can see something like 20 or 30% speed up for some applications, and for other applications you can see a slowdown. So we don't tend to heavily use it on HPC systems, but it is used, and it's used for various things. Quite commonly, people will use it for things like if they do an I/O server for their application, so that they run an extra thread or an extra process, which is doing different kinds of work than their main program. So it could be handling I/O that's been offloaded. Then they run that on the hyperthread, and because it's doing different operations, it can overlap quite nicely. Or you can handle, you can offload some communication functionality that sends messages to other workers onto the hyperthread, and because that's doing different things to your main computational simulation thing, then that works as well. We also have another thing which we're not going to cover in this course, but we should all be aware of, and that's accelerators. And so, it's very common for HPC systems to have another bit of hardware alongside the processor that's focused just on doing floating point operations. And here we're talking about GPUs, but it can be other things as well. These are very, these can be very useful for applications, but ARCHER2 doesn't have them because not all applications can exploit them. And so we've kept ARCHER2 as general purpose as possible, so it's as widely available to all applications. There's a subset of applications which just don't port well to GPUs. But for a wide range of applications, then GPUs are very sensible, particularly machine learning as well these days. And so they can be heavily used to optimize applications as well. There you've got to care about things like the overheads of moving data to and from the GPU. And in a similar way, you have to worry about the overheads of moving data to and from a processor. And so there can be a lot of work to optimize, making sure that you're not stalling on data accesses as well. So yeah, we've got this idea of cache memory, which we've been through a little bit. I mean, these numbers are all a bit out of date, but we have this idea of different levels of caches and different speeds of memory accesses, and this is what we have for ARCHER2 and all modern processors. In general, as I said, all this is handled for you by the hardware. Making sure your program structure maps well to the cache structure is sensible to get you best performance, because the compiler and the hardware can only do so much and rearrange your instructions to get data reuse to cache. And so you have to write your application in an efficient manner as well. There is extended functionality often to allow you to do clever things if you know your data mapping patterns in your application. So there's a thing called prefetching, which is populating the cache with data before you need it. And of course, this can be really beneficial because if that can happen whilst other work's going on, then you can effectively use your data in the cache without having to wait for it to come from main memory at all. Now, modern processors will have prefetching hardware in them which detect basic memory access patterns and preload data based on that. But you can also, if you have a memory access pattern in your application which is regular but won't be recognized by a processor, it is also possible to put prefetch instructions into that manually to get the performance there as well. So that's something else you can look at, and I've seen quite nice work by others on doing prefetching of data in the previous loop cycle to have it ready for the next loop cycle as we go along. As I said, caches generally work on the principle of locality, so temporal or spatial locality, and so what happens is a cache line, when data is loaded into the processor, it first gets loaded into the cache, and you don't just load the data item you need, you load a whole cache line, which is generally sort of 16 data items or 32 data items. And because they're already loaded in, they stay in the cache. It's likely they'll be reused because applications often reuse data multiple times once they've loaded it. And it's also likely that data that's close to it in the cache line will also be reused, so that we can exploit the fact that we load whole lines of data in there to get better performance. And of course, this is great for us for computational simulation, where we generally have large arrays and we iterate through those arrays in a particular order. And so once we load a cache line up, we've got a chunk of the array, and as long as our access patterns match that chunk of the array, then we can reuse that data inside the cache without having to load it up every time. Caches are, yes, there's some complexity in caches. We don't need to go into too much detail, but in reality, caches are split up into units of data, which we call a line or a block, and that will be, somewhere between 32 to 128 bytes, 256 bytes maybe these days. And when a program instruction asks for some data which is not already in cache, it will be loaded up. Caches actually get quite complicated because they have to both be simple and efficient, and so the hardware has to choose some way of loading data from memory into a place in the cache it can find, and it also has to choose a way of keeping data in that cache if possible, right? And because this has to be done in hardware, it can't be a complex algorithm that does it. So what we generally have is this idea of cache sets, and each set is given a number, and then every part of memory maps to a particular set. So in this case, we've got 512 sets, and then so every part of memory will map to there. And that means multiple bits of your memory map to the same set, which is fine, but that's how it works. And then when you load in a new bit of data, it will replace some data that exists in the cache already. And generally you place some data inside your set, but those sets are not, they have a certain size, so a set may have 8 entries in it, and then there'll be some algorithm to choose which bit of that set to replace, and that may be a least recently used bit, so it will throw out the old bit of data, the bit of data that's least recently been accessed. But there are other functionalities that go on here. Now, why do we go through all this detail here? Because it can matter for performance, right? So, caches are interesting. There's lots of complexity in how they're implemented and how they work. Most of that is hidden from me, and most of that you don't have to care about. But there are times where understanding the size of sets and the size of the cache can let you optimize your data access patterns in an application. Again, this is more advanced optimization, it's more, once we fix all the basic things, can we come back and look at those kind of things. But it's worth understanding a little bit, and we haven't gone through it in huge detail, but you can go back through the slides at your leisure, exactly how these caches work, because that can impact the performance you can see from your application using that cache. The main thing to do is make sure you exploit the cache, and then you can optimize later on different making sure you're using the cache as efficiently as possible. And in that, there are also things you care about when data is written, write through and write back caches and these kind of things. You can also build programs which ignore the cache for some things. We do things called streaming writes and stuff like that, and they can all be potential optimization points. But the cache is just there to stop the processor slowing down. And so if a processor goes and runs an instruction which asks from data that's not in the cache, we get what's called a cache miss. And then that means we're going to have to wait for that data to come into the cache before we can run, and that will slow our processor down. It will drain the pipeline down, all those kind of things. So we want to have as few cache misses as possible in our application. We can also have much more expensive operations that happen every so often as well, what we call page faults. And this gets even more complicated, but this is to do with how application memory is organized and utilized. And actually, there's a virtual memory system which splits up the physical memory space into pages. And when a new page has to be created for an application, that can create a bigger delay. It gets done in software, and it's called a page fault. Now, again, most applications you won't see problems with this, because for most applications you pay your cost for your page faults all at the beginning, and then you don't really see them again after that. But there can be some ways of writing code and running code that can cause page faults to be more common, and then we'd have to look at your memory management in the application and making sure that we're reusing memory as much as possible rather than creating new memory. And part of that is tied up in something called the TLB, the translation look-aside buffer, which is the thing which maps the virtual memory into physical memory. Again, this gets quite complicated and is quite involved. At an introductory level, we wouldn't expect you to have to deal with TLB and TLB misses, except for saying that there are also some scenarios where an application performance can be damaged by TLB misses as well. And so we can have these memory performance issues in various places: at cache level, cache reuse level, page level, and translation look-aside buffer level. They can all be fixed in programs by changing memory access patterns if possible, or by changing the size of pages we use on the system. And both of those are sensible optimization techniques we can use for our applications. We've talked about prefetching a little bit, as I say, prefetching again is a bit more of an advanced optimization, but can definitely be used to improve performance. And then we also, now we won't go into this in any detail at all, there is also a interaction between cache and cache performance and the other workers on our processor, so the other cores on our processor. Because the cache stores a temporary version of our data taken from main memory, we need to make sure that if other workers, like in a parallel application, are trying to use the same data, they haven't gone to main memory and got an old version of that data, because we've got the new version in our cache. And so processors implement what we call cache coherency protocols, which maintain that the coherency of the data across all the cores on the processor, if that's been loaded in locally. And so there are a number of ways that this is done in the hardware, which again you don't need to care about, but it does mean that there can be scenarios, particularly when you do parallel applications, well, only when you're doing parallel applications like OpenMP on a node, where you can end up with the performance being impacted because this cache coherency functionality triggers memory operations that are not actually necessary because the processor thinks that you're sharing data between workers on different cores when you're not actually. This is called false sharing, and it comes about because you have these cache lines which are bigger than individual data elements, and so one worker could be working on part of a cache line and another worker could be working on another part of a cache line, but as long as those cache lines are in the same, the same cache lines and they've got the same mapping to memory, they will invalidate each other's data and constantly force memory traffic to go backwards and forwards and really slow down the processes. So that can be an example of one of the ways that all this hardware and this nice functionality in the processor that's provided for you that you don't care about, you don't have to care about, can impact your performance. And one of the ways we look to do to fix that, and we look to optimize applications, is by looking at our code, seeing if that's possible, profiling our code, seeing out what performance we're getting on the hardware, seeing what hardware counters tell us about things like cache misses, TLB misses, memory traffic, and then coming back and saying, okay, it looks like I've got this kind of problem here, can I fix it? Finally, we have this idea of distributed memory in our nodes. So ARCHER2 has two processors per node. Each one of those has some memory attached to it. And the time to access the memory attached to the processor my program's running on is different from the time to access the memory on the other processor in the node. This is what we call a non-uniform memory access time, non-uniform memory architecture. And so on ARCHER2, we have two processors. Each has 64 gigabytes, sorry, each has 128 gigabytes of memory. The whole node has 256 gigabytes of memory, and any core from any processor can access all the memory. But actually, it's faster for my core on this left processor to access the local memory attached to it than it is to go across this infinity fabric and access the memory attached over here. So we can have performance impacts from memory locations as well. Now, in general, if a worker here creates some data, it will, by default, be created in its local memory, and so will be as fast as possible, unless this worker is trying to create so much data that it doesn't fit in this local memory at all, and it will spill across here, or the local memory is already full, but this memory over here is not full, and so it will create it over here. And unless you're doing something like an OpenMP parallel program, where, for instance, you have workers all part of the same program but go across all cores, but say the first worker creates all the memory for everybody and then everybody else uses it, and then it will create all the memory locally to here, and even the workers over here will have to use that memory over here. So this memory locality, just like we need to use the caches efficiently and make sure we're reusing that cache data as where possible, and we need to make sure we don't get these false sharings where different workers in our parallel application think we're working on the same bit of data when we're not, because that creates lots of memory traffic across the cache. We also have to be careful if we're doing things where individual workers are sharing data across the node, that we make sure that it's primarily created in the memory which is local to the worker which is going to use it the most. Again, most of the false sharing and CC NUMA stuff Mark will cover tomorrow in the OpenMP lectures, because it's mainly concerned with parallel use of these nodes inside a threaded application like OpenMP. Okay, so what does our actual hardware look like? We're using in ARCHER2 AMD EPYC 7742 processors, 64 cores per processor, with a 2.25 gigahertz base frequency. Actually, that's been dropped recently to 2 gigahertz, so you can push it back up if you want. Each one of those cores, 64 cores, has 2 floating point units. And each floating point unit can do a fuse multiply add instruction at once. So you can effectively do a large number of floating point operations, because each floating point unit is 256-bit wide vectors, so it can do 4 double precision, 4 64-bit numbers instructions at once. Each unit can. We've got 2 units, so it can do 8 floating point numbers at once. And actually, if you can utilize this special fuse multiply add instruction, which does a multiply and an add in a single cycle, then you can actually do 16 floating point operations at once. But of course, that depends on your code being able to vectorize, and it depends on your code having multiplies and adds in similar places in the application that can exploit that. So not all applications will get to that performance level. So theoretically, each processor can do about 2.3 teraflops, tera floating point operations per second, and each node can do about 4.6 tera floating point operations per second, teraflops. But of course, that relies on that vectorization and that fuse multiply add. So if you can't fuse multiply add, then you'll only get half that theoretical performance. And if you can't vectorize at all, you'll get a 16th of that performance. So you can see already this performance, even not considering the memory and the cache and things, if we can't do the vectorization properly, then we get a big performance hit on that. The AMD processors also do symmetric multi-threading or hyper-threading, so you can run 2 threads per core, and that's turned on, but by default, the way we submit jobs, you generally don't use for hyper-threads, but you can if you want to submit and use those hyper-threads. Just for complete detail, although we probably won't use any of this data in the course, each core has a L1 cache with 32 kilobytes, 8-way set associative with 64-byte lines. And there's an L2 cache in the cores as well, which is 512 kilobytes, so it'll be slower, but it's bigger, 8-way set associative and 64-byte lines. And then each 4 cores, which AMD call a CCX, a compute module, I think, has a shared L3 cache. Question?
Yeah. Are these caches write through or write back caches?
That is a good question. I think they are right back, but I will check.
Okay, thank you.
I think they're right back. Then there's each 4 cores share an L3 cache, and that's a bigger 16 megabyte cache, but it means that you've got this sort of interaction between groups of 4 cores where they're sharing some resources. Now this can be good from an OpenMP perspective for sharing data between workers, but it can also mean that your applications can, if they're doing different things at different times, can impact each other as well. There is 256 gigabytes of main memory per node in 8 NUMA regions. So there's 8. So each processor has 4 regions of memory, where there's slightly different memory access costs between them. And you can get about 3 gigabytes a second per core if all the cores are used. So the overall processor has quite high memory bandwidth, but because we've got so many cores on there, we don't have huge memory bandwidth per thing. And if you're interested, the latencies are for the L1 cache, L2 cache, L3 cache, and main memory are below. So 4 to 8 cycles for L1 cache, 12 cycles for L2 cache, 39 cycles for L3 cache, and about 270 cycles for your closest memory to get data from there. Now, yeah, as we've already said, this NUMA stuff, this non-uniform memory access cost is important, and these processors has not just, it's more expensive to go across processors, but there are more expensive memory accesses inside the processor as well. So making sure that your data is local to your cores can be quite important for performance. Most of the time, this will happen for you if you just run a large-scale parallel application, but there are times where we need to make our applications aware of this for good performance. Either if you're doing hybrid codes, that's an MPI plus an OpenMP code, or if we're just doing pure OpenMP codes on the node. and if we're underpopulating for memory reasons. So I'll come to your question in a minute, but underpopulating means we run less things on the node than we have cores. So I've got 128 cores, but I only run 8 workers because I need more memory per worker than I would get if I filled up the node. That's underpopulating. But if I do that, I need to make sure I put my workers not on the first 8 cores, but spread them out across the node to get all that memory access and that proper memory bandwidth, and to stop us interacting on the L3 cache and those kind of things. Okay, so as per normal, we're slightly behind schedule. That's okay. As I say, we've got time to catch up, particularly in the afternoon. We're a big chunk of time to do with practical, so we don't need to worry too much about that now. I know there's a lot of detail in there. There's a lot of detail which is not particularly specific. I mean, there's some very specific detail about the processes here. We don't expect you at this point to be able to exploit very much of that. We just want to give you the background information and the background detail to set us up for the rest of the course. Are there any questions at this point? If not, in fact, I should have a look. There's yeah. I think so. Now on the timetable, we have a break for half an hour. I think that's probably good. You probably do need a break from me speaking to you for too long. So we'll do a break for half an hour. We'll come back. We'll kick off the practical, and then we'll get into the next lecture. And as I say, if you've got any questions in the meantime, please do let me know. But back at 11:30, and then we'll take it from there. Okay, so what we'd like to do, I think, is try a first practical exercise, which is, let me stop sharing this at the moment. If we share the practical notes instead. So here I'm on the GitHub, but you can download the PDF if you'd rather. We have to get onto the system. So logging on through an SSH account to the system. If you've not got an account already and things, then send me a message or let me know. We can sort that out. There is a bunch of instructions at the end of this document about if you're not used to running on systems like ARCHER2 or remote HPC systems like this, then there's a bit more guidance in the end about different things you can do. What we would like to do, so when you log into the system, if you're using an account with this project we've set up for this course, that's going to be under the TA091 project. When you log in, you'll log into somewhere called work TA091, TA091, and then your account name, because that'll be on the work file system. The work file system is where we sort of store things we want backed up, but not things that we want to use in production on the compute nodes, because it's not accessible from the compute nodes. So what we want you to do when you log in is move on to the work file system by using this command here and replacing account name with your username. As I say, any of this doesn't make sense, and please let me know. I'll give a little demonstration after this. And then run this command here to copy the source code archive, which has all the source code we're going to have in it. I'm going to use for the applications, an example, sorry. And then run this command to unpack it, so this tar command here. So copy and then tar extract the single node optimization file. And then when we've done that, what we want to do is run this this first exercise, which is investigate the performance variation across cores on ARCHER2 nodes. Okay, so here we're looking at memory bandwidth and looking at that non-NUMA form memory architecture performance costs. And we're going to run a little program called Streams, which is a memory benchmark. And in its current formation, it should be set up to run on 16 cores on a single chiplet, so inside a single NUMA region. The batch script first runs another program called XTHI, which it just prints out where things are running. And so you run it, and then you can play around with the configuration to change whether you run inside a single NUMA region or to run across NUMA regions by editing this command here, this srun command here, and see if you get performance difference there. And you can then instead of running on 16 processors, run on 32, 64, and 128, and see what kind of performance you get. So this is just to give a little feeling for how the performance of a memory, because Streams is a memory bandwidth benchmark, how that varies by some of these issues we've been highlighting, and just to get you on the system and so you can run jobs and things here. Now the batch, you can use the reservation here, so sbatch and this reservation command here. I need to look out what the actual reservation number is, so you don't use XXX there, use something else. Let me go and have a look at that. I'll put that into the chat, and then we can take that from there. Any questions? As I say, I'll go for a little demo as well. You don't need to use the Cray compiler, but you can use the Cray compiler. So when it first, that's a good question actually, Chris. Let me check what the source code is expecting. By default, it'll be expecting the Cray compiler. So I've not explained to all of you here, but we have 3 compilers available on ARCHER2. We have a Cray compiler, which is the one you get by default when you first log in. We also have the GNU compilers, so GCC and G-Fortran, and we have the AMD compilers, so AOCC. They are described in a little bit more detail here, down here, in the handout practical notes. So you can do this module load. By default, the Cray compilers are loaded, so when you log in, you have this prog n for Cray, but you can also try the GNU compilers and the AOCC compilers as well. Let me just have a look, Chris, at whether there are specific flags in there which are Cray only. I'll just log on to ARCHER2. Let me stop my sharing and share my terminal. So I'm just going to change the settings on this so it's more readable when it comes through. Okay, so that's not terrible, is it? So I'm not using your project. I'm using this is my standard account. You can see that by default, when I've logged in, my username is Adrian J, and I've logged into a directory called home Z19 Z19 Adrian J. You'll log into one that's home TA091 TA091, and then your username. I want to go to my work file system, which is exactly the same, but just has work at the front. There. And then I want to do this, copy this command. So copy Z19 shared sno.tar to here. And then I want to run this command. And then I can log in here. So now I've got this directory. It's creating this directory called ARCHER2 opt, and I can go into the placement directory. Now let me just see what compilers I've got loaded. So I've got the Cray compilers loaded by default. And so if I type make here, no, ignore that. This is a problem I have with my setup. So it's a problem with using my account for this, but I've messed up my setup for various reasons. You wouldn't have seen that. So if I type make here, then you'll get an executable that's built. Looking at that, Chris, it depends if you want to do, so it's placement, it's C. I think those commands will work with all the compilers, apart from maybe -F freestanding. So if I did a module load prog and GNU, so the GNU compiler works as well. Yeah, so all of them actually should work for this. So the Cray compilers are default, but that shouldn't matter. You should be able to do with the GNU compilers if you want, or the ARCHER compilers. Okay, so that's generated me this program called distributed streams, and we should see we have a batch script called run streams. Now, I also haven't said here, you need to edit this batch script to change this here so I think that should be TA091. Everything else is set up as by default. We're using one node. We've asked for 20 minutes. We won't need 20 minutes. We're running one task per node. We're running that node exclusively, so nothing else can use that node. And we're running on the standard partitions and quality of service things. And then down here, we're running in one NUMA region with 16 processors, not using the hyperthreads, and distributing our processors in a round robin fashion, or in a linear fashion. And then we run this little program first, which says, what was my configuration? How was I run? And because it's using the same set of srun commands, it will have the same distribution as this program here. And then we run the actual streams program at the end there to actually benchmark the memory and see what performance we get. Hopefully that makes sense. Now let me just give a quick check on what the reservations are. Okay, so the reservation for today is catchily titled TA091_858976. Don't worry, I shall put this into the chat. So when you submit with that command, icebatch reservation, you would put that code in here. I'll just type this out so you can see it. And I'm going to put this into the other place we can do the chat in as well there. What's it called? The pad. Okay. Now, one of the challenges of running this kind of a course online is I can't see how well you're getting on. So do let me know if you're having any problems, if you're managing to run or not managing to run. Let me know. It'd be useful to see what's going on. Okay, well, that's my fault. So I think what you then need to do, and apologies for that, is to change this line to that line. See if that fixes it for you. Good. Sorry about that. That's my fault. Is this, if you don't run it with a reservation, if you're not running in a project account, then you don't need that QoS. If you are running with a reservation, then you need that QoS. Yeah, anybody else having any other problems getting access to the system, and feel free to send me a message. You can also send me a private message here as well, so it doesn't have to involve everybody. It's possible to send me a private message as well. But just let me know how you're getting on. That looks like a lovely output error message. Let me see if I can replicate this. Did you get any other output, Kristen?
Can you hear me, please? Oh, can you hear me?
I can, yep.
Okay.
I can.
So
I can hear you, yeah. Sorry.
Okay, so there is, like, it looks like it's normal output until the few final lines.
Okay, so for now, ignore that error. I'll try and work
Okay.
out why that's going on, but for now, ignore that.
I actually have the same issue, but I guess that it's no big issue.
Yeah, maybe I'll have a look. It probably means I've done something wrong in the code, but as long as you get the benchmark output, like the bandwidth numbers, it doesn't matter.
Yeah, there's a copy scale, try it, and so on and so forth.
Yeah. So that's what you should need. Let me just check. It should look something like these are old ones that I've run in the past, but it should look something like in fact, I get the same. There we go. It should look something like. So this is an example where I'm running. Actually, I think I'm running on 32 processors here, but this is the XTHI output at the beginning here, which says, process 31, MPI rank 31 is running on core 31, which is what we want to see. And then we have some memory bandwidth tasks. So this is individual. The first set of rows is individual process memory bandwidth. How much does a individual worker out of my 32 workers get? And it will do average, max, and min across the workers. And then the next 4 lines is summing that up sensibly across the workers. So on the node as a whole, I got 50 gigabytes a second, or average, or 56 gigabytes a second, and each worker got on average 1.7 gigabytes a second. So that's the average. Yeah, so apologies for that, but ignore these slides at the bottom here. I'll work out why that is, but it shouldn't impact what you can actually do with the practical at the moment. But thanks for letting me know. Okay, so here's an example of me running this, just in case you've not quite got through it yourselves. But when I first ran it with this one here, actually this was run a long time ago, but I'm running 32 workers. But I'm running those 32 workers all on the first 32 cores of the node, which means they'll all be on the first processor and just using 2 of those NUMA regions. So they're just using, there's 8 NUMA regions in a node, they're just using a quarter of the node resources. And that means that my total across my whole application, I can only get at most about 56 gigabytes a second of data bandwidth into memory. So by restricting myself to those particular nodes, I can access all the memory, but I can't get the high memory bandwidth that I would have normally. Whereas if I run in the second time round here, I'm still running 32 workers, but I've actually told it with my srun command here, -C4, that says give each worker 4 cores, and I want to run 32 workers. And so that's going to spread them across the node. So you can see the first worker has cores 0 to 3, and the second worker has cores 4 to 7, etc., etc., all the way up to core 127. So that's using all the physical cores in the node. And now you can see here that I'm getting up to 120, about 120 gigabytes a second, give or take, on the node to get that performance. So I'm still using the same node. I'm just using it slightly different way. I'm using it spreading out across all the cores. It's probably also possible to get even higher bandwidth, I think, by going up to just slightly underpopulating, but we'll see. But that's the idea here, is just to show you the difference. So now most of the time, most applications will use all the cores, so the differences won't be particularly, it won't occur or won't be this big. But there are cases where you can get a quarter of the memory bandwidth performance by just configuring your job to run in slightly the wrong or less performant way. So let's have a look at this. Okay, so I need the 32. So I've gone down to 16 workers here, 1 per every 8 core, and I've got better performance than I got when I had the 32 workers just using the first 32 cores, but I'm still not managing to get the full memory bandwidth from the node. So I've only got about half the memory bandwidth from the node there. And then if I went down to 2 cores per worker and up to 64 workers, let's see how that goes. So now you can see again, I've got more workers. They've got, they've only got 2 cores each, all the way up there. And you can see now with 64 workers, I can get a bit higher bandwidth actually. So I'm up to about 230 gigabytes a second on the average bandwidth across the node. So it just shows you that there is a variation in the amount of performance you can get out of the memory system here, and that depends on how you place your workers, but also how many workers you have. So the overall node has a total memory bandwidth, but you can only get to that total memory bandwidth by using a reasonable number of workers. In this case, at least 64 workers out of 128 in the node. So those are some of the kind of, particularly with the parallel programs, there's kind of configuration, performance optimization things you can do without even changing your application, but just making sure you're using the hardware in the correct way. Do let me know if you want any more explanation or want to found something different or want to discuss anything. I appreciate that maybe not all of you have finished running this practical. That's fine, and we've got time to come back to this. But I think I'll move on to the next lecture if that's okay. But as I say, do let me know if you've got any questions or still want to do some continuing work.
So I'm just curious that if I catch it correctly, that you get higher bandwidth with 32 workers, and I would expect that the best bandwidth would be with one processor, one worker per NUMA domain. So why is that?
So it's to do with how the memory system is set up. There are restrictions on how many memory instructions can be issued by each core at the same time. So the bandwidth doesn't scale by that NUMA domain. It scales by something that's slightly smaller than that. So particularly for these for streams anyway. I mean, there are different memory configurations where you could do better with slightly fewer workers. But basically, because of the instruction issue and the memory subsystems of each core, an individual core cannot drive the full memory bandwidth of the NUMA domain. We need multiple cores to get to that full memory bandwidth of that NUMA domain.
So is it something specific on the Archer system, or is it specific to this particular stream benchmark, or?
Well, it's something particular to this processor, this set of processors, so the AMD EPYCs, and the memory we have attached to them. But it's also something that's it is dependent on the benchmark that's used as well, a little bit. So it depends exactly what kind of memory access patterns you have. Stream is pretty linear, right? There's no reuse. We've got no cache in here, but the prefetching works quite well. So it's sort of a tests the main memory bandwidth without any intermediate caching most of the time. Although on this, there's probably some write back interference. So you could improve something by doing non-temporal stores or something like that. But yeah, that's pretty much. It's just showing what the processor itself can achieve at a bulk level. Yeah. So as Mark says, you need a sort of a minimum number to get close to peak bandwidth, but to actually get the peak bandwidth, so to get the actual peak bandwidth, you really need a slightly higher number than 2 per core as well, per region. It depends exactly how you use them. Okay, I'm just going to share. Any other questions? I'm just going to share the slides whilst you ask them. Okay, that should have come through now. So now we're going to move away from the hardware and the optimization. We're going to talk about profiling. And that's because, key to optimizing applications on any hardware is understanding their existing performance and understanding where the bottlenecks or issues are. So the way we do that is through profiling. This is using, again, 1 second, I've opened the wrong. I think I've opened slightly bit older. Oh no. Just get the correct slide deck up. Bear with me, I will be there in a second. And it should be coming back through just now. Okay, so yes, profiling lets us find out where time is being spent in our program when we run it on a particular system. But it also lets us investigate other things as well. So we can investigate hardware counters and which tell us something about how efficient the hardware is being used. And if you go at a higher level, things like network communications or I/O for things like store accessing data or doing MPI communications between nodes as well. So there are profiling tools which will do all of these things. Fundamentally, what we were looking to do is say we want to work out if our application is performing well to start with. Maybe that you've got a good application and it's probably doing as well as you're going to get out of a system, or at least can you quantify how close to getting good performance out of the system is. And as I said before, it's likely that most applications get nowhere near the peak performance of a floating point performance of a hardware system like ARCHER2 or any modern hardware system. And then then we're going to have to look at then, okay, if it's not getting the best performance we could possibly get out of this system, where is the time being spent? Where is the work that we're going to do to optimize this code? Where is it best being focused? So there's no point trying to make a part of the code go much faster if actually it only takes 5% of the runtime, because even if we make that part of the code go 1,000,000 times faster, we're only ever going to speed up our application by 5% overall. So that's what we use profiling for. It's a look before you leap code approach. Code profiling is as I say, the main thing we're going to do, particularly in this course, and we're looking to do basic profiling. We can do by actually letting the compiler add some functionality into our code to track what's going on there. So the compiler will do what we call instrument the code, and then when it runs, it will generate some extra data to say what parts of the code were being run at what time, and we can use that to look at where the time is being spent in the code. So the nice thing about that is it's we don't have to change our code to do this. We just turn a compiler flag on and it'll add the extra functionality to it. The downside is that it impacts performance. So it's not something we want to do all the time because it makes the code slow because it's adding extra stuff in there. Okay, but it's when we want to do the profiling, we want to turn it on and we want to run it. Standard profiling will do return data on the amount of function calls, so the number of times a function is called, and the amount of time spent in various parts of the code. And then we can go into more detail with more specific compiling or profiling and profiling tools that will let you look at things like cache misses, TLB misses, cache reuse, floating point operation rates, instruction retiral rates, instruction issue rates. So you can get some much more fine-grained detail from the processor about what it's doing. But by default, that's not where you start. By default, you would start with what's my application actually doing? We'll take it from there, and then you could look at things like the cache miss rate for a particular part of the code, if that's what you're interested in. For standard profiling, there's actually two ways of doing this. There's what we call sampling and there's tracing. So sampling is every so often interrupting the program when it's running and asking where the program is in the code. So the program counter, which is the thing that the processor keeps track of where it is in the code, gets investigated every so many times a second. So something like 100 times a second, the program will be stopped, the program's counter location will be sampled and recorded, and then the program will move on. So this is reasonably low overheads, add 10, 15, 5, 10, 15% to runtime, but it'll get you an overall sort of large scale picture of where the time is being spent in your application. So a statistical picture of which routines are spending most of the time. Of course, to be able to do this accurately, the code needs to run for a reasonable amount of time. So, sub 10 seconds, sub 5 seconds is probably not long enough for a complicated code to pick up all the nuances of it. And it can also miss some things, right? So the sampling, if you've got lots of small functions happening all the time, and the sampling won't pick all those things up. There is a more detailed mode you can run in as well for some profilers called tracing, which really records much higher level data for every function call that happens. So rather than just sampling every so often, it says, every function that starts and finishes, record the start and finish time. This is more invasive, so it's a higher overhead, and can also produce very large amounts of data. So it's not where we generally start with profiling to start with, but it can give you more detail for a small run of an application. And the standard Unix, I would say Linux nowadays, but the standard profilers we have are called prof and gprof, very imaginatively named. And their flags to enable them on standard compilers are -p and -pg. Okay, so literally all you do is you add an extra flag in here, the -p to enable output for prof, and -pg to enable output for gprof. And this will, so you have to rebuild your code, you have to make clean and then add these flags on. You have to delete all the object files and recreate them with these flags enabled to generate the functionality. But then when you run your program, you'll get a file called gmon.out or mon.out, and that contains the profiling data where you can use the program gprof or prof to look at it. So you would, I've created my program here. This is my executable. I ran it, it produced a gmon.out file, and then I can run gprof, my prog. It goes and looks for the gmon.out, and then it displays it for me. And the difference between prof and gprof is just the level of detail that it records. So prof is pretty high level detail, which is just a sample of all the function calls it's picked up over time with no relationship between them. So you can see here I've run a small program. I've not run it for very long, so obviously I'm breaking my own rules there. At most I've run it for about 2 seconds. But then it tells me each of the functions in my application, how many times that function was called, how long it ran for, and what percentage of a runtime that was. Okay, and so even with this very basic output on a small program, I can get some information out of it. As you can see, I've got 2 main functions, relax and resID, which are taking about 60% of the runtime, and then I've got some other stuff going on down here. Now, some of these are functions that I've written. This is a Fortran program, by the way, but so that would change the outputs. Some of these functions are written, so I've written relax, I've written resID. They've got underscores appended to them, but or post appended to them, but that's the functions I've written. But these things down here are functions that I haven't written. So some of these are library functions. I can see this here, F90 close, F90 SLR I4. These are probably functions to do with I/O. So this is opening or closing and reading or writing a file. So I can see probably about 15–20% of my time is spent in the file I/O as well here. And then there's this thing called mcount, and this is actually the overhead of the profiler. So the mcount routine is something that the compiler inputted to added to my executable to create the profile and data. So that's the overhead of my machine. So you can see on this one it took about 6%. It was about a 6% overhead for this run. Worth knowing that if this thing here actually is much higher up my profile, then it's likely a indication that you've got lots of small function calls that happen often, which are impacting the performance. And it may also not just be called mcount, it might be called monitor or mon_control or any of these kind of things. But that's the thing. gprof, so that's a prof output. gprof is the same, but it also produces a program of call trees sorted by inclusive time. So you can say how much was spent in this function and how much was spent in this function's children. So you can get some kind of overall feeling for where in the program this is being spent as well. So if you've got a function that's called from many places, you can start to assign that to the places it's being called from. And if you can, you can really break down and have a look in a bit more detail about where in your program structure the time is mainly being spent. When we're doing profiling, this is there's a sort of a process we want to follow. So when we come to performance optimization, we always want to profile our codes. We don't want to believe either what people tell us or what we think about the code, even if we've written the code, because we could easily be wrong about where the hardware has been spent, that the time is being spent on the hardware. We want to make sure we profile on the hardware we want to run on. So there's no point profiling on my laptop if I'm going to run on ARCHER2 because I've got a different processor on my laptop. So some of the bulk information might be similar, but some of the specific details will definitely be different. Ideally, profile your code using a full-size problem or a problem which is of sensible size, because some of the issues you can run into performance for applications can only surface when you run up to production sizes in their codes as well. And in general, this performance optimization and profiling loop should be sensible. It should be repeated as you're going along. So it's not a one-stage process. You don't profile, optimize, and then you're done. Generally, profile, you optimize your code, then you reprofile it to see where you're at, and then maybe optimize again in a cycle until you get to a point where you're happy enough or you've run out of time to do that as well. So there's a question here. Is gprof output readable for OpenMP and MPI parallel or MPI parallel runs as well? Okay, so gprof here, as we're showing you, is definitely a serial application. You can get the same kind of outputs from OpenMP runs because they are one process, but a bunch of threads. They won't necessarily be as accurate. I don't know if Mark's still around. Mark is much more of an expert on OpenMP profiling than I am, but you can generally get some level of profiling with the OpenMP stuff. When we want to go to parallel applications, we then need to move on to a more involved profiler, a profiler written especially for parallel applications. So on ARCHER2, we would use Cray. There's also other profiles available. There are linear ones, but so the ARM are linear profilers. There's also the Scholastica and profilers from Vampire and Vampire Trace. So there's a bunch which will do the same thing, but collect the data across all the processes, all the threads that are running, and then display you on an aggregate and a thread or process level as well. So we'll come on to see CrayPat, which does the same thing, but for parallel applications. But fundamentally, it's built and operated in a very similar way to this gprof idea. So that nicely moved into the parallel profiling stage, which is to use a slightly more functional and designed with parallel in mind profiler. And on ARCHER2 we have Cray, which is Cray's profile and tracing tool, and it lets us do profiling across MPI processors and OpenMP processors and these kind of things. And so what you do is you can do this in both modes. You can do it in tracing or in sampling mode. So basically, the preferred mode of running Cray is to run it with a basic instrumentation to do sampling. You get a basic profile out of that. And then if you're interested in more of the details, you can rerun it in a tracing format for the whole code or for subsections of code to get more detail out of that here. So we use a module to get Cray on up and running here, and I need to check this hasn't changed actually since I last did this, but I think module load perf tools light is the way we generally go, and this is the basic sampling profiling, and then we don't have to change our compiler flags here. We just rebuild the application with this module loaded, and that will automatically have updated the compiler to turn on the profiling. And then we run our application and we get a performance file out the end, which we can then use to visualize. So here's an old example, but an example of the kind of thing you get out of Cray. This is the command line output. You can also visualize some of this stuff in a graphical user interface as well. But you can see you get something very similar to the gprof output, actually, I haven't shown you, where we've got profile by function, total. It tells us actually for this one's 55% of the runtime was in MPI, and then it breaks down the MPI function calls we had, and then 42% of the runtime was in user functions, and then it tells me which one of those user functions was the most expensive and how often they were called, and then how much time was spent in library or system functions as well. And it gives us also the gprof style output where we can say which particular functions called what other functions, and it can also give us a line by line breakdown when we do the more detailed profiling, where actually 3% of it was in this line here and 3% of it was in that line there. So you can go right down to the individual line level to see where the performance has been to. And once you've got the data, there's various different reports you can build, so the callers and source, call tree and source and other things. So there's lots of functionality we can do there. Once we've done that initial sampling profile, we can do a more detailed one by using this automatic profile analysis functionality it has, where you do this process called pat build, use a function called pat build to take your executable and rebuild a new version of it, and then you'll get some more detailed information off the back of that, and then you can use some of the output that gives you to build a even more detailed profile of the expensive parts of your code, and so that's the kind of things we can do here. There's lots of detail here. It's all documented reasonably well on the ARCHER2 website, and in also the practical we're going to do next. So you can go through some of that detail there, and it should hopefully make more sense when presenting it on the slides. Key to this kind of performance optimization on a single node, particularly if we're not focused on the API stuff, we're looking at sort of hotspots for the code, paying attention to the parts of the code which are consuming significant portions of runtime if we're lucky enough to have them. I mean, one of the challenges with optimization for real codes is that quite often you'll have lots of areas of the code which are equally as expensive, so you can end up with 4 or 5 or 6 or 7 places each taking 10% of the time, and then you have to worry about which ones you choose to optimize and which ones given a finite amount of time to optimize the applications. It can be a little bit more tricky. But the nice thing about Cray is it will also give us access to some of the hardware counters as well. So things like L1 and L2 cache misses, use of vector instructions and those kind of things. Cray has mechanisms for finding hotspots in routines. So you can do even more detailed evaluation of functional of loops inside functions and subroutines using this H profile with the Cray compiler, H profile generate, and that will look at those kind of things to give you a bit more detail on that kind of functionality as well. And we can start to get with a more detailed profile than CrayPat some of this hardware details as well here. So we can see, and again, this is generic, this is not specific to ARCHER2 here, so some of these will change if you run it on ARCHER2. But you can see here, there's a breakdown of an individual function. 25% of that function was the runtime of the whole program. There's some discussion about imbalance time. Well, this is for parallel application, so this is how much did this vary across the different workers. And then there's how many times was this function called, and then L1, L2 cache metrics. These are floating point or vector metrics, so how many times we've got vector metrics. And then from that, CrayPat has built us some derived metrics to say things like, what's your total number of double precision floating point operations? What's your level 2 cache miss hit ratio? And what's your bandwidth between level 2 and level 1 cache, and these kind of things here. And so we can use that to get much more in-depth information about the routines that you care about in your application. Yeah, so CrayPat, it's a good question, but CrayPat is, as it says in the name, a Cray tool. So this is not available particularly outside Cray, HPE Cray systems. There are other profilers that do similar kinds of things for similar systems, though. So if you're running on an Intel system, there's Intel vTune, which is freely available these days, which will give you similar kinds of information for your for systems that can support that. Intel processors is what it's designed for. But as I say, there are things like Scholastica, which will do your bulk level profiling, but doesn't particularly go into the hardware level details. And then there are other tools which will do the hardware level details. So my brain is letting me down here, but the people who make Scholastica and some of the German universities also have some other profiling tools from there, which do similar kinds of things. We have a set of courses on the ARCHER2 website, which are particularly focused on profiling tools. So let me just remind myself, because we get the experts who write the tools to come across and give those. And so there's things on that have been on ARMForge, which is the linear tools for doing some of that profiling, which is also available. But I'm just trying to find the most recent one. There was a performance analysis workshop in May, which looked at things like Scholastica, which will work on other systems. And Scorpy, that was the other one, Scholastica and Scorpy. Thanks, Mark. Which will give you other tools there. Now, fair enough. That's interesting to know, Bjorn. Yeah, so there are other tools that are out there, and there is training on the ARCHER2 website for some of those other tools, which can have a look. But whether Cray will ever release it to work on other systems, I've no. Well, whether HPE, I don't know. I know they have some containerized versions of it which can run in various places, but I don't know how well it integrates with other systems. And theoretically, I think it should be it shouldn't rely on very much of its Cray anymore. But I guess it's part of Cray's software advantage to keep this to themselves, unfortunately. But if you have any sort of questions, further questions or information you want on some of these other profilers, then do let me Yeah, so the Scholastica stuff is reasonably yeah, okay, so sorry, this is the Intel tools on AMD processors. Intel tools will run on AMD processors. The AMD processors don't have all the performance counters that Intel VTune is looking for to get its proper analysis. Cray have obviously done the work to plug into the AMD performance counters that are there, and Intel haven't, for obvious reasons, haven't done the same amount of work. So Intel VTune can get you the things. You can also get the performance counters yourself in a more low-level way using a programming interface called PAPI. But then you're going to have to do the analysis yourself as well. So you can collect the data, but you're going to have to do the analysis yourself as well. Thanks for all the questions, though. Yeah, Liquid's great as well. So interestingly, so I've used Intel Trace for other systems. I've not used it on ARCHER2, but it is available on ARCHER2 in a roundabout way. And one of my colleagues was trying it the other day. I'll have to ask her how she got on with it. Theoretically, I think it will work, but you need to use Intel MPI rather than Cray MPI to do it, I think, which may have some issues in terms of performance anyway, on ARCHER2. Intel Trace is not bad elsewhere. So is Vampire Trace. I think you might have to pay for Vampire Trace. I'll move on anyway, but it's good questions. So the hardware counters, CrayPat will give you hardware counters, which give you extra information on what's going on, like we've seen here, some of these things here. The AMD processors we have actually don't have a large number of counters compared to the Intel ones we've had in the past, but you can still access them and you can pull out the data from them. So when we're doing that with CrayPat, we use this special environment variable pat RT perf counters, and we specify what groups we want to collect. You can have a look at what groups are available in these different ways. There's pat help, then counters and Roman groups, or there's man HWPC, or you can cat this file here, and that will tell you what hardware counters are available. Basically, there will be a summary with a TLB activity. There's a summary with branch activity. You can get memory bandwidth. You can get memory bandwidth stalls and cycles, and you can get what instructions have been dispatched and stalled as well. So this is an example of using CrayPat to get memory bandwidth from the hardware. It's interesting. It's an interesting question, George. Yeah. So CrayPat will help you in that regards, but so your code is generating C code from Python level extractions. I mean, one of the things you could do is it starts to get complicated actually. There are some examples out there, yeah. I mean, you could modify the JIT compilation process to add in the compiler flags you need. Then you're going to get a lot of disparate information out on the profilers, lots of different profiling data. Yes, there are other tools that may be sensible to do to give you this kind of performance information. X-Ray, I've not looked at X-Ray or Paraver, Radim, but yeah, I'll have a look and have a think about that. Yeah, I mean, this is one of the challenges for DSL. So domain-specific language are typically quite hard to profile and to get accurate and to debug. In fact, my main problem with domain-specific languages is debugging them, because if something goes wrong, it's always hard to work out where that's going wrong in. But I agree, there's definitely a space for generating profiling information from domain-specific languages where you're going for an intermediate stage where the user's not compiling it.
Actually, the benefit of the X-ray over, for example, Scala is that it enables the tracing of the binaries, so you don't need a recompilation.
Okay, cool. So that may be an option. That may be an option. In the same way that yeah, okay. Cray requires recompilation actually, so it doesn't even it too actually requires recompilation. You just don't have to change your. So Radim was saying his X-ray paraview was the option, which is he's got a answer slightly higher up in the chat, George. Which I think Barcelona tools have X-ray. Yeah, Barcelona tools. Okay, so this is an example of the kind of memory bandwidth profiling you can get out. So here's a function sweepy, and then this is general summary of the function, and then we've got L2 cache, so the data cache, miss ratio and hit ratio, and the bandwidth between them there. So we can see actually here we've got quite a low L2 cache hit rate, and we may want to do something in our application to try and optimize that kind of thing. Cray gives you performance numbers in general, which are average across all the ranks, and that's why you don't always get integer values for some things. It will say, you've retired 24.7 instructions. Of course, you can't retire a 0.7 of instruction, but that's because not all ranks do the same amount of work. So if you want actually to get individual data for each rank, you can also filter that out. So you can actually say, I don't want to get all the data here, I just want some of it, and you can use these filtering conditions to only get every second rank or everything, the first 1024 ranks, or those kind of things. So if you're running an application which has got very varied workloads across its workers, you can do something like that with CrayPat to collect the data you want rather than go and aggregate. That's a good question. So the DRAM bandwidth, I don't think we get performance counters for the DRAM bandwidth. Let me just check. Oh no, we get memory bandwidth counters. So yes, there will be performance counters for the memory bandwidth. I'm just not showing you all the data here. I've just picked out a particular part of the data here. So you should be able to get DRAM bandwidth as well from those memory counters, I think. At least last time I played with it, I'm sure I had some memory bandwidth counters. But you can have a play around with the profiler yourself in a little bit and have a look. Someone wanted to say something?
Yeah, just if those memory bandwidth counters are based on the L3 cache misses or really the DRAM counters.
Well, it's definitely not based on DRAM counters. I think it's based on, from my understanding, it's based on the memory controller counters rather than DRAM. So we're not sampling DRAM counters here, but each processor has a memory controller in it, which is talking to the memory, obviously. And I think what we're getting there is the counters from that. But we'll need to go and have a look in more detail to get that. Beyond, we also have problems that have had and have problems with perf event paranoid equals 0 or 1 or 2 as well, particularly on other systems. But that can stop you collecting performance data because the Linux kernel restricts access to performance counters on the CPU because they can be used for exploits on the CPU, and so for a lot of systems that data is locked out. Unfortunately, but for ARCHER2 we do have access through this profiling functionality. I should have said as well, it's not in the slides, but there are other tools you can use. There's a tool called perf, which is a general Linux tool. And that can give you, as long as you have access to the hardware counters, that can give you similar kinds of information and has quite a nice environment or suite of reports for a range of applications. Now, it's not designed for parallel computing, it's designed for single processes, single programs, but it can be quite a nice little performance investigating tool as well, perf, if it's available. Okay, CrayPat also has functionality built in for OpenMP stuff to collect information and profile data on your OpenMP regions. So you can be shown per thread rather than per process. And you can build that with tracing. You can even do OpenMP tracing by adding an extra flag when you do the CrayPat stuff. Now, for the Cray compilers, we should get those tracing points automatically. For the AMD GNU compilers, you may need to intervene in the code to do that kind of thing. And it will tell you things about loading balance and those kind of things for the OpenMP stuff. CrayPat will also report on memory usage, so what amount of memory is used, not bandwidth but capacity. And you can look at that across processes and across your whole program as well. So that can be useful. And that will tell you things about how much memory is used per rank, how many allocates and frees have we got a memory leaks, and those kind of things. So that can be useful. And Cray have a viewing tool called Apprentice2, which lets you navigate some of your program, this information graphically as well. It's not anything particularly amazing, but it is available. And there are versions you can install locally, so you can copy your profiles back from ARCHER2 to your local system and run Apprentice there as well. So profiling is what we need to do to guide our optimization. Profiling is essential to identify performance bottlenecks. And there are a range of profilers out there, a few of which we explored in the discussions, but CrayPat is the one that's default on ARCHER2, and that has quite nice functionality for parallel systems as well as for the non-parallel stuff. But key to performance optimization is making sure you can do your profile and you understand and analyze your profile data before you do your performance optimizations, because at least then you can understand how efficient your application is, how well it's using the nodes, and then optimize from there. There's something that we haven't included in this course. People often do is something called a roofline analysis, which is to take their code, to profile it, and then work out, compared to the memory bandwidth and the floating point operations your node can do, how well is it doing, and then that will show you how much scope there is for optimization if you can change your code to do any of that stuff. And you can do a little bit. There's a little tool. Actually, I need to update for some of the newer AMD counters. So for some of the AMD counters, where you can automatically do some roofline analysis of things on a system like ARCHER2, on a Cray system, using some of the CrayPat functionality. I need to fix some of the counters in there because some of them are a bit are not quite correct yet, but I can provide details of that if anyone's interested. Okay, so any questions? I know that people have had some great questions on the way, but any other questions or any general questions or comments? Okay, yeah, sounds good. Sounds good. Yeah, and if we can do collaborative with Hawk, is always welcome as well yeah, because they're very similar systems in some ways, but different systems in other ways. It's always interesting to see. Yeah, okay, so if there's no other active questions, then there's another practical we can do now. which is actually a slightly separate practical. So let me just share the practical exercise screen instead. So stop sharing, share application or screen. So here, see here, exercise 2 in our handout says CrayPat. The code for this exercise is in ARCHER2 opt VH01. Please follow separate instructions in the CrayPat intro. So this is actually a practical provided by Cray themselves. So if you go back to the exercises, we'll see there's a CrayPat intro here. And if we click on that, we'll get a different PDF which guides you through running this example through CrayPat and giving us a feeling for how to do profiling using CrayPat on ARCHER2. Looking at, I seem to remember actually, you may need to, so this particular thing here, it says module load Cray netcdf, module load Cray HDF5. There may be a thing where you need to swap those around and do the HDF5 load first before the netcdf one if that doesn't work. But other than that, you should be able to follow this through. We may also need to change the batch script like we did in the last one and have a look at that. Other than that, you should be able to run this profile on ARCHER2 to get the data out and be able to analyze this particular application as it's outlined in this PDF here. So if you're still wanting to do the streams benchmark, that's perfectly fine. You finish that off. If you've got any questions or comments about that, please. Otherwise, you can move on to this profiling practical. And then let me just see how far behind we are on the timetable. Okay, so this practical was going to run from now till 1, and we'll stop at 1 UK time, which may be 2 for you in Europe, for a break. Because we've only got 10 minutes now, I'll give you a little bit more time. So if we come back at 2, I'll be around here until 1, and then if we come back at 2, and we'll do another 15 minutes of the practical, and then we'll go on to the lecture in the afternoon, and then we'll go on to the more involved practical after that. Any questions? Okay, well, let me know how you get on, and if you've got any problems, if I've made any mistakes with the batch scripts or anything like that, then just let me know, and we will fix them. Otherwise, any questions, drop them in here or give me a shout.